So welcome to part 3 of lecture 21. I know the first two parts have been kind of heavy on the theory, and so I thought I would spend a little bit of time in the next two parts just kind of working out an example, going through it slowly so you can see some of the ideas that we've talked about in today's lecture with respect to the nilpotent operators. So the example I want to look at is I want to look at this map given by sending x, y, z to 2x plus 2y plus z, 5x plus y minus 3z, and x plus 5y minus 3z. And my claim is that this is a nilpotent operator. Okay. So first of all, how would you even see this? Well, luckily, for this particular example, you can actually just use matrix operations to check. Okay, and how could you see this? Well, even just using any of the bases, so we might as well use the standard basis, the matrix associated to this operator is 2, 2, minus 2, 5, 1, minus 3, and 1, 5, minus 3. So this is the matrix associated with respect to this standard basis. And now, what is the matrix associated to the cube of this power? So to check whether this is a nilpotent operator, we just need to show that t to the cubed is the same thing as the 0 operator. And that's because the dimension of r cubed is 3. Now, by the properties that we know about the matrix associated to an operator, we know that this is the same thing as taking the matrix that we started with and raising it to the third power. And you could do this by hand or go punch it into a computer program, but when you do this, you'll find that you get the 0 matrix. Right? So this here would imply that t cubed is nilpotent because it has the same matrix as the 0 operator. Okay, so we know that it's a nilpotent operator, and this is one way to check. But now let's say we wanted to kind of like use the previous result, right? We want to find a basis so that it has a form of the previous theorem. So this matrix clearly doesn't have the form of zeros on the lower left-hand side. So how should we do that? Well, believe it or not, kind of embedded in this proof is really an algorithm in order to find the basis, right? So really, you go back to here, you find the dimension of the null space of n. Then you extend it to find the dimension of the null space of n squared, and so on. So what you need to do is first find all of these spaces, okay? And here you use just some linear algebra from Math 1B03. And I'm going to skip some of the steps because I'm assuming that you guys are pros at this. So here I have my matrix, and I can row reduce my matrix. I can put it into this form. And if you stare at it for a second using some linear algebra from Math 1B03, you know that this matrix is spanned by the vector 1, 1, and 2. Okay, so that's the first fact that we have, and I feel like I'm missing a minus 3 here, and I am. There should be a minus 3 right there in order for this to work. Now I'm writing everything in terms of vectors, kind of as column vectors. Okay, so that's good. Now, remember, we also need to know what are the null space of the operator squared and then the operator of the cube. Okay, so we can do the same thing. We know that the matrix of the square of this operator is the same thing as taking the square of the matrix. And you can crank this out any way that you want. You'll end up with this matrix. So there's the matrix you get. And you can row reduce it. So you get that this is equivalent to 3 minus 1 minus 1 and 0, 0, 0, 0, 0, 0. And, you know, using techniques from 1B, okay. So from 1B03, let's see if I left myself enough room at the top here. Oh, I actually did a lot of the work here. I'm just repeating myself. Via 1B, we know that the null space of t squared is equal to the span of the two vectors 1/3, 1, 0, and the vector 1/3, 0, and 1. And so now kind of remember, though, that this is not the basis of t squared we want. when we did our proof, what we wanted to do was we wanted to extend the basis of null t to the basis of null t squared. So we have a basis for null t squared, and we have our basis for null t. So the way that you do this, all right, is you take the vector that we know of the null space of the first power, so which is 1, 1, and 2. And then we can add the basis elements for the null space of the second one. But the point is that these guys are no longer linearly independent, but you can actually find a linearly independent basis where this is the first one. And then this guy here is actually the second basis element. So 1/3, 1, 0. So there we go. We've extended the basis from null t to null t squared. Now we also know that null t cubed is equal to r cubed. So now we want to kind of extend this basis to a basis of R3, right? And if you stare at this for a second, you can actually see that it's kind of clear about which vector we're missing. We're missing the first standard basis element, right? So if this is equal to the span of the vectors 1, 1, 2, 1/3, 1, 0, and 1, 0, 0. So this is a basis for null t cubed. And notice that we've kind of extended the basis. So this is a basis for null t. These guys here is a basis for null t squared. And then everything here is a basis for null t cubed. So we're just following the procedure within the proof, but we're applying it to a specific example. And when we come back, I want to show you that this actually show you in more detail why this is the desired basis of V.